Aditya, I had reported your matter to the admin, so let us wait for the response.
Thank you, sir.
So meanwhile, if you have any questions, let me know, or comments or questions or whatever, until we wait for others to join. So who is the CR for your class?
Sir, I am Kshitij, sir.
Kshitij, yes, I think you had written a mail to me. I remember that, yes.
Yes, sir.
Sir?
Yes.
Hello, sir. Sir, in
Yeah.
Moodle, sir, you enabled that introduction portal, but there is nothing inside that file, folder, sir.
Oh, I think I might have by mistake enabled something else. Okay, I will do that.
Okay.
I'm trying to enable that now. Let me. I think I by mistake I enabled the wrong one. So where is the PDF? Okay. When was the last class? 23rd, is it?
Sir, Monday.
Monday is 23rd or 24th?
23rd.
Sir, 23rd.
Okay. So one of you, can you check in the Moodle, is it enabled now? I did something. No, it's not changing.
It is still restricted.
Yeah, it's not changing the year. I'm doing it. I think I did this. It's not allowing me to change the year. In the sense, allowing in the sense I change it, but it does not reflect. Maybe I will remove the red.
Sir, maybe because of the date.
Okay, I removed it. Just a moment. I will just come. Someone is at the door.
Sir, we are able to see the introduction presentation now.
Yeah, sorry. I'm back now. Okay, so I will do it. I'll try it later. So meanwhile, let us come back to the class. So let us look at some of the historical aspects. We were looking at some basics of definitions of navigation, guidance, and control. So navigation is estimating the position where we are. For that, we require coordinate systems. We will go into that in the next class. And then guidance is something identifying the path if you are given the source and the destination. So the guidance path, what you did use will depend on the application at hand. You may minimize the distance, fuel, or with respect to some constraints, you may have to optimize your path. So the control is nothing but the steering commands, which also includes the thrust levels also. But for most of the rocket applications, if they use solid thrust boosters, then the thrust level is fixed. It's only the direction that is counting. If you have liquid engines, then and throttleable engines, then you can also vary the thrust. Today we will look at some of the historical types of navigation, what people were using in the past, and then what we will be using in the future. So there is something called pilotage or coastal navigation. You look at the familiar landscapes and then move. That was the historical one. Then there is something called celestial navigation, where if you are in the sea, you will be observing certain stars and then navigating. And then there is electronic navigation, where you use radar or GPS, or radio navigation is anyway related to both of them. Then dead reckoning is something in which if you know the acceleration and the initial position, then you can compute by double integration, which is also called as autonomous navigation, which we will discuss, which is an important navigation aspect or type in the, it's also called as inertial navigation. Yes. So pilotage, you use the visual reference either on the ground or sea. You might have heard of these lighthouses used by the ships, used for guiding vessels or so many other things. So this is one of the most ancient techniques which were used. So celestial navigation is something where the positions of the stars or sun or moon, whatever that is used for estimating the positions. You can understand where the latitude is if you observe the pole star, but longitude is something difficult where you need to understand the local time. You have to observe when the sun is going to be on the meridian. So typically it is used by the ancients for sea navigations. Now, one of the important things that is needed here is you need to estimate the angles of these objects in the sky. So there are instruments to do that, so which is usually done. For instance, if you know the angle made by the pole star with respect to the horizon, you can get the longitude. And if you know the local time, then you can estimate what longitude you are in. Sorry, the other one was latitude. For local time, it is the longitude. Then in the case of, I'm simply skimming through because these are just introductory things. Then in the case of electronic navigation, you use radio frequencies. If you use a directional antenna, then the direction, if you have many sources of radiation, then if you can receive from a particular direction, then you can understand from which direction it is. Of course, you have to encode it to understand which different frequencies can represent different directions. That is one possibility. Or in the case of radar, you have to measure how long the radio waves have traveled. So if you can estimate that, then you can find out the position with respect to the object which is transmitting. And then in the case of velocity, you can use the Doppler shift. A moving object will shift the frequency of the radiation. Then radar navigation is actually closely related to that. GPS is the navigation system which most of you are using it. If time permits, we will also discuss basics of GPS navigation in the class. So dead reckoning is an important navigation which is used in the all your missiles and spacecrafts. It is basically estimating where you are by knowing where you were earlier. In addition to that, you have to estimate what is the speed and the time. So it is actually DEAD is not that really dead. It is actually deduced reckoning, DED, from which this has come, but people still use this terminology. So that is deducing the position by estimating something. The difficulty here is if your sensors are performing poorly, then your estimates will also be wrong. So this is one of the most difficult thing. It has been observed that some of the animals do use it to a primitive level, and many marine navigation, air navigation uses this inertial navigation. So when you have GPS signal is not available in the underground or something, sometimes in the automotive vehicles also the dead reckoning is used. So, and in your phone, there is something called pedometer. So when you walk, it will count how many steps you have placed. So that also has an accelerometer actually, which is also called the speedometer, which is used to find out the number of steps. So in use with the software, it is called as the speedometer. Sorry, press the end key suddenly. Okay, so what are the different navigation systems used in the launch vehicles? So let us see our different cases. In the case of launch vehicles like GSLV, PSLV, or in the case of satellites, you require a different kind of navigation mechanism. So basically, launch vehicles, if you first we have to understand how the vehicle moves. So how does the rocket move? We use the thruster. If anyone has questions, don't hesitate to stop me. I'm going a little fast because these are all very basic concepts.
Sir,
Yes,
sir, in Dead Reckoning, how only speed and time can help us? Shouldn't we know the direction also? Because
yes.
there are.
That is also required. You are right, exactly right. So if you know the speed in a particular speed is not enough. You need to know the velocity. You are right.
Okay, sir.
Yeah, thank you for that. In your car, basically you know the speed, and from that speed you estimate the position, distance. So it is not exactly where you are; it's only the distance you have traveled. You are exactly right. So we need
Okay,
to
sir.
know the direction also. We will come to that. Thank you for mentioning. So if you have the difficulty, let us look at the launch vehicles and its issues. One of the difficulties: how do you move the rocket up in free space? We cannot use wheels because there is nothing to catch or hold on to. So exhaust gas from the tails, which we all know, will be used to move the rocket. By basically, the basic principle is the Newton's third law. So, and then the difficulty here is how do you stabilize the rocket? You have to imagine that if you have a long stick, if you are trying to balance on your hand, how do you stabilize it? So you have to move your hand from the bottom to make sure that the stick does not fall down. So it's also called inverted pendulum problem, stabilizing a rocket. So you have to fire the thrusters in such a direction such that the tilt is compensated. So that is the requirement for steering a rocket. That is some kind of gimbals are provided or sometimes thrust vectoring. Thrust vectoring basically means changing the direction of the gas flow by firing one more smaller set of thrusters. I think these videos are not visible here. So let me open it in a different.
Sir, hello.
Yes,
Sir, the use of magnetic compass is in which kind of navigation? Like,
on terrestrial navigation, you can use magnetic compass.
yes.
Yeah. So usually, yeah, it's a good point. I have not mentioned it. Magnetic compass can be used to understand the direction north and south, or of course, it is magnetic north and magnetic south. Let me show a video. Just hold on to a moment. Are you seeing my screen?
Loading, sir.
No, sir, it
No,
is
sir. So
black.
it's black.
Yes, dark.
Maybe if I play, it will become white. Are you seeing something now?
No, sir.
No, sir.
Okay, so what I will do is these videos may not be visible here. So I will be uploading it in the what is that Moodle, so you can watch it from there. So basically, okay, let me share that slide.
From YouTube, maybe you can show in Chrome tab.
Okay, so I will. It is from YouTube, but I do not know where it is now. I had some time back. Maybe I can search now. Yeah, that's a good point. Let me search. Just hold on to a moment. Good point. I think next time I should load those YouTube videos and keep them. Yeah, there is an advertisement coming. Just wait. Okay, I will share it now. But this is something other than what I. Something else. But at least, of course, it is very similar to. Are you seeing the screen now?
No, sir. Yes, yes, sir. That's visible. Yes, sir.
Yeah, it's basically this. You can see that when he holds the thing, so he has to move the bottom part to keep the stick straight. So you have to do something similar in the rocket launch vehicle also. So at the bottom, you have to fire the thrusters in different directions to keep the launch vehicle straight. So this is the thing which I wanted to tell you. But I think there's a different video. It doesn't matter. The concept is similar. Okay, so I'll pause it now. Is there any question? So this is what is happening. If you have to keep something long object straight that is balanced, you have to fire the thrusters in certain direction. So let us also see what happens in the rocket. We will search for a rocket gimbal control. This is sometimes called thrust vectoring. I have to see. Yeah, you can see. Let me show this one. Are you seeing this screen now?
Yes, sir.
Yeah, you can see this movement of the rocket thrusters. Are you seeing it? This is called gimbaling the rocket thrusters. So if multiple thrusters are firing, when your rocket is moving up, you have to move this thing in certain direction. Remember that you cannot move to a large degree. This is hardly 3 degrees or something, or maybe more, up to 5 degrees. So usually our launch vehicles will have very less ability to move these things, at most 3 degrees or something. So right now probably this one appears to be 6 degrees overall approximately, but of course we don't know. You have to read the specifications. Because every depending on the design, in this particular case he has shown through engines can move, all the engines can be moved. You can see that the other one behind is also moving. Okay, yeah, that's all. I think now he will move the one which is towards us also. So you have to imagine these engines have to be moved when the rocket, the thrusters are fired. So that is the difficulty, to even have engines which can withstand that temperature, as well as these bearings are still working. Okay, I'm pausing now. This is called gimbal movement. This is what is done in a rocket to keep it vertical when it is moving, vertical or any specific direction you want. Now let me stop this one and then go back to the Chrome tab we were discussing. Okay, so this is balancing the rocket visa, steering the rocket engine gimbal. I have also uploaded the some other videos, may not be the same one what I showed, so you can use that as reference. So how do you understand where the rocket is? So this is, that is called, we are looking at navigating the rocket. We don't means navigation, guidance and control at the moment, because our course, the interest in our present course is only identifying the position where we are. So there is something called inertial navigation, which is closely related to dead reckoning. If you know the direction of the movement and then the speed at which you are moving or acceleration in that direction, you will be able to integrate and then find out the position where you are by knowing where you were when you started. So that is called autonomous navigation, which is very important in the case of missiles, because once you fire it, it should not request ground support for it to reach the destination. Then you have non-inertial navigation, which is also called GNSS, we will say Global Navigation Satellite Systems. So this is usually used in the modern spacecrafts now, because these GPS systems are now available. So one important difference you have to know notice is the launch vehicles and rockets or spacecrafts are moving at very high velocity. So your whatever GPS systems are running in your mobile phone will not be able to sustain this. So when you are moving at very high velocity, the Doppler shift is very high. Your carrier frequency will be shifted to a large extent. So you need special techniques to understand what is happening when the velocities are very large. So your system has to be very fast to recognize these fast motions. So then you have an integrated navigation system, which is used in all the modern, especially the Western launch vehicles. They use the GPS system and integrate it with the autonomous navigation. So whenever GPS signals are available, the signals from that is used to estimate the position. And then when the signals are not available, during those periods of time, the autonomous navigation, which is using the inertial sensors, estimating the acceleration and the orientation, you will be able to combine these two to get a better accuracy. So if you think of it, if you have an automobile and you are passing under the bridge, so under the bridge the GPS signals will not be available, but your automobile system will be able to show the position relatively well. So there this integrated navigation is used. While you are when the signals are available, you are using the standard GPS navigation. When it's not available, by estimating the speed, either through inertial system or through odometers, you will be able to identify the position. So this is what is done in the automobile, and also modern launch vehicles also does this. So we will be looking at basics of these things. So inertial navigation is basically this. As one of you pointed out, it is very closely related to dead reckoning. You need the position and the velocity. So position, velocity and direction are estimated by some sensors. So the position and velocity are estimated using the computers. Then you have the motion sensors called accelerometers, which estimate the acceleration. and then you have rotation sensors which are called gyroscopes. So these do not require any external signals. You should remember that the motion sensors, accelerometers, and rotation sensors do not require any external signals. Without that, it can estimate the acceleration and the rotation rates. So you look at this block diagram, that is something called set of gyroscopes, which will tell you what is the rotation rate. The symbol omega is rotation rate. Actually, the rotation rate is known in the body frame. We will once we reach that, we will tell what this body frame and other thing. Body frame basically means rotation with respect to the frame in which the body is. So if you have a rigid body and if you draw fixed orthogonal axis onto the rigid body, and then if that fixed orthogonal axis moves with the rigid body, then you call it as a body frame. So the rotation sensors are placed attached onto the body. So that is why it is called as the rotation body frame. The body rates or the body measurements. Then you also have accelerometers, which are similarly placed in the orthogonal directions and attached to the body. So as the body changes its direction, the sensors also change the direction. So therefore, these measurements are called body rates and body accelerometers, accelerations. So together, the gyroscopes and accelerometers are called as the inertial measuring unit. It's only a measuring unit. And then when you include navigation equations, we will see what these equations are. We will be dealing with this in detail as we go along. You will be able to estimate the velocity, then the attitude. Attitude basically means the orientation. How to define the orientation, that is roll, pitch, and yaw. We will discuss this as we go further. Then the horizontal position as well as the height or the depth. So this is what forms the inertial navigation system. So the inertial navigation system will put together the gyroscopes, accelerometers, and then the navigation equations and the computers, which will finally give you the output as velocity, orientation, and then the horizontal position and depth. Any questions here? This is an important concept. It's only a concept now. We will be going into the details as we move further. So
Sir, here attitude means what?
orientation.
Okay, sir.
Direction.
Okay, sir.
Sir, what is IMU?
Inertial measuring unit.
Okay, sir.
They measure inertial parameters. Inertial parameters are your rotation rate and acceleration. Inertial navigation system is together with IMU and computers and the equations, you are getting the navigation solution. It is called as this system, complete system is called as the inertial navigation system. Inertial because inertial parameters are rotation rates and accelerations. So one has to understand what is an inertial frame. Can one of you? Inertial frame, non-inertial frame. We will be discussing this, but just
there's
before.
no acceleration is inertial.
Yeah. So if it is acceleration is present, you will be able to detect it. So that is why accelerometers are required. No acceleration. Yes. And rotation is also a kind of acceleration, but rotation sensors are separately available to measure. Yes. Someone was saying something.
No, sir.
Yeah. So there is linear acceleration, that is your thing. Then you have rotatory acceleration is the rotatory motion. So we will be discussing the definitions of them as we move along. So Earth is an inertial frame or non-inertial frame?
Non-inertial.
Non-inertial.
Why is that?
It is accelerating, like around the sun it is revolving. So this is
Whenever there's Rotation or revolution, there's acceleration towards some center.
Yes, yes, very good. So there is rotation as well as, yeah, because of that there is an acceleration. Right. So therefore, on the Earth also, if you have inertial sensors, these inertial sensors will be making some measurements. There is one more difficulty here. What would happen is, if you these accelerometers will also be able to sense acceleration due to gravity. So what is acceleration due to gravity on the surface of the Earth approximately?
9.8 meters.
9.8.
Yes, so your accelerometers will actually be measuring 9.8 meters. So if you keep on integrating, what will happen? It will appear as if the object is moving, even though the object is on the surface of the Earth. So the inertial sensor, especially the accelerometers, cannot differentiate between acceleration due to gravity and the actual acceleration when you fire the thrusters. So this is one difficulty which you will encounter in the navigation in the launch vehicles. So you have to compensate for it. So you have to know what the acceleration due to gravity is. Then you have to subtract, or basically subtract that component and then compute the navigation solution. Otherwise you will get an erroneous value. So that is called gravity compensation. But as you move to different heights, the gravity component is different. The acceleration due to gravity is different. So you need a model, that is mathematical model around the Earth or in the neighborhood of the Earth of what this gravity model is. So once you have this mathematical model, you can apply the compensation after you do the measurement. So this is one important thing which is done in all launch vehicles. So this is one mathematical model which is required. So that is called gravity compensation. So let us look at, there are two main kinds of inertial navigation, something called a stabilized platform system and then the strap down system. So the name indicates stabilized platform in the sense the sensors are placed on a platform which is stable in spite of the movement of the vehicle. In the case of strap down system, the inertial sensors are mounted onto the body of the system itself. So let us look at the figure, a schematic figure. So you imagine a series of gimbals. So you have the black object which I am indicating through my mouse is the mounting frame. That means on the body this object is mounted. And then you have this, don't worry about the motors now. So you have this ring, the first outermost ring is free to move along the axis which is shown here. That is along this mounting axis. Mounting axis, you can see a straight line. With respect to the mounting axis, this outer gimbal is free to rotate. Then on this outer gimbal, you have one set of inner gimbal. So whose axis is along the north? So along the east axis, the directions are shown above. Along the east axis, this is just an direction, okay? As your vehicle move, all this number will change. For this figure, you can imagine this. The east axis is the mounting axis, north axis is the inner gimbal axis, and then there is a V axis where the inertial sensors are mounted onto the platform. So the inner gimbal is free to move with respect to the north axis. And then the stabilized platform, there is a platform inside. This platform is free to move with respect to the V axis. So any questions with respect to the motion? If you understand this mechanical structure, then whatever I discuss now will become easy.
So this V-axis is can change, right?
Yeah, right now you don't worry about the change. Just at any point of time, This is the set of axes.
Okay, sir.
Yeah, they will change. You are right. At a particular point of time, instead of any point, I will say at a particular point of time, you imagine this situation. So let us first assume that these whatever axis along which what we indicated, you have a frictionless bearing. Frictionless bearing means what would happen? You imagine along the east axis, suppose the launch, launch vehicle is rotating with respect to E axis. Then what would happen? The outer ring, will it move along the east axis? You imagine this object is placed inside a rocket. On the walls of the rocket, you are connecting the dark colored thing.
Outer ring won't move, sir.
The outer ring will not move. In fact, nothing moves because of that. Because the object is rotating along the east axis, nothing inside moves. The outer ring will not move since and the inner ring as well as the stabilized platform does not move. Do you agree with that?
So the mounting frame is rotating, right?
Yeah, frame will rotate.
Okay, sir.
But it's a frictionless thing. It's a hypothetical thing. Later on, we will see how to overcome this frictionless. That is why these motors are shown. We will come to that later. For the first,
The outer ring will also rotate, right?
pardon me.
The outer ring.
Outer ring will not rotate. That is the thing we are discussing now. The launch vehicle is rotating along the east axis, but it's a frictionless bearing, which is here. This silver colored thing are frictionless bearing. So if it is frictionless, what would happen? The launch vehicle is rotating, but this ring will not rotate. First, this is the main thing we have to understand.
Okay.
Similarly, if the launch vehicle moves along the north axis, that is rotates along the north axis, rotates with respect to the north axis, then the inner gimbal will not rotate, but the outer gimbal would have rotated. Okay, the inner gimbal will not rotate. Do you agree with that? Assuming it's a frictionless.
Yes, sir.
Okay. So similarly, if the launch vehicle rotates only with respect to the V axis, then the stabilized platform will not rotate. Everything else would have been rotating. Imagine the launch vehicle is rotating along the V axis. Kind of roll you can imagine, assuming the launch vehicle is pointing in the V direction and it is rolling. Then what would happen? The black objects will move around. Then this ring, the inner bearing also will rotate. But what would happen? Because the inner gimbal, the innermost gimbal where the platform is connected, it is a frictionless thing. That thing will be in the same orientation. Is that accepted?
Yes, sir.
So when the outer ring does not rotate, the platform is stable. When the inner ring does not rotate, the platform is stable. Even when the rocket rotates in the V axis, the platform is stable. That means this platform will be stable irrespective of any rotation of the object. So this is the main intention in this design. That is, if you have this frictionless set of systems, then the inner platform can be kept stable. So if you have accelerometers there, then you will get acceleration. In which direction? So that let us try to estimate. Suppose along each of the bearing, you have an encoder. Encoder means it will estimate what is the angle by which the object has rotated. Rotatory encoder. Along each of the bearings, let us, in addition to being frictionless, let us introduce the rotatory encoders. Let us start with the outermost ring. Suppose the launch vehicle rotates in the east axis, the encoder will measure the amount of rotation angle. If you know the angle, you know the direction. Similarly, if the launch vehicle rotates in the north direction, if we had placed a rotatory encoder in the north axis inner gimbals, then the angle by which it has rotated in the north direction can be measured. In addition, let us also place one more rotatory encoder in the innermost part where the platform is connected. So when the launch vehicle rotates in the V axis, then the angle by which it has rotated can be measured with respect to the V axis. So therefore, for any movement of the launch vehicle, the angle in which the launch vehicle is moving can be directly computed by measuring this rotatory encoder. Is that okay? So in the ideal situation, with frictionless motors and rotatory encoders, the angle or the direction of the motion of the vehicle can be tracked. And then the acceleration can be tracked by measuring the accelerometers from the acceleration meters, which is present in the centermost table. This is the ideal situation. So the angles are measured by the rotatory encoders, and then the acceleration is measured by the stable platform inside. So what is the acceleration? So with respect to which frame are the accelerometers measuring these accelerations? It is with respect to the initial frame in which the object was initiated. You had initialized the system somewhere. Okay, with respect to that orientation, all the acceleration is computed. Is that clear?
Yes, sir.
Yes, sir.
So, the inertial navigation basically, in order to find out the position, what is required is the acceleration with respect to the initial frame. Because once the frame starts changing, if you are going to get the acceleration, then that cannot be used to compute the navigation solution directly. So you imagine an XYZ initial frame, and then if you know the acceleration with respect to that frame in how the acceleration is coming, then you can double integrate and find out the position in the space. So that is what this ideal gimbal or stabilized platform system does. So if this concept is clear, the next one will be straightforward. The non-ideal one is just how to compensate for the non-ideality.
Sir, it is only measuring the rotation angle, right? How will it measure the acceleration?
Acceleration accelerometers are there now in the platform. So rotation angle is to know the orientation only. Actually, to know the position, only accelerometer values are enough.
Okay, sir.
Is this clear? Any questions? Don't hesitate, because these are fundamental concepts. Once these concepts are clear, then everything else is just mathematics or some numbers only. That's what we will be dealing with in future. Okay. So now let us think just one more concept and I will stop. I think time is getting over. So now you imagine the bearings are not frictionless. If it is not frictionless, what will happen? In the sense, it is as low friction as possible. There is some coefficient of friction. So along the east direction, if the rocket rotates, what would happen is, instead of this outer ring being in the same location, the outer ring also will rotate. Is that clear?
Yes.
So now you imagine this: if the outer ring rotates, the platform is not stable now. The platform also rotates inside. But you have placed gyroscopes. The gyroscopes will measure what is the rotation that is happening with respect to the outer ring. So using that rotation, you use something called as the roll motor. The roll motor will compensate for this rotation to bring it back to the stable direction. So that means you have to do this faster than the sensing rate of the accelerometers. For your navigation solution, let us assume that every 100 milliseconds you need the acceleration values. What you will do is your innermost rotatory thing should be some 10 times or 100 times faster, so that whenever these accelerations are measured, the platform will be almost in the stable direction. That is the initial orientation. So due to the coefficient of friction, all these gimbals will encounter small changes in rotation when the rocket is moving in the when the rocket is rotating in the east, north, and V direction. So these are compensated by making the measurements using the innermost gyros and then fed back to the roll motor to bring it back to the original direction. So this is called servoing. You might have heard of the servo motors, no? Servoing basically means to keep the position same even when other things are changing by looking at the errors in the motion. You look at smaller errors which are occurring and then you compensate it by going back to the zero position, whatever that initial zero position is. So if this servoing can be done sufficiently fast, then whatever your accelerometers are measuring can be taken as reasonably good values for computing your navigation solution. So this is precisely what is done in the gimbaled or stabilized platform system, and the navigation solutions are computed like that. So these were even in the first, all your older launch vehicles, historically, they were using gimbal system. And then even the first moon mission used the gimbal system. There are some difficulties, later on we will discuss about that. So this is the basics. So if you have any questions, let me know. I will be stopping the class after this.
Sir, how do you know how much to compensate? Like
the gyro is measuring, no? Gyroscopes is measuring the rotation rate. So you have to compensate for that rotation rate that has occurred by rolling the motor in the opposite direction.
sir, like because of friction, there is some additional rotation rate, and because
Yes.
of normal rotation of the engine, there is some rotation. So how do you know which rotation corresponds to what?
No, the gyroscopes, inner gyroscopes will measure only the frictional quantity. Otherwise, the platform is stable, no? If the
Okay, sir.
bearings are frictionless, the platform was stable. The rotation is only due to friction.
Okay, sir.
You have to carefully calibrate this during the initial test itself. On the ground itself, these calibrations are made to make sure that you are able to quickly compensate for that. The friction coefficient has to be computed. So these inner gyroscopes are precisely doing that. And you need very sensitive inner gyroscopes. Even smallest moment has to be measured. But
Okay,
one
sir.
advantage is the gyroscopes need not have wide dynamical range. It's only that friction compensation only it has to do.
Okay, sir.
Yeah, good question. Yeah, any questions? I think your other class will start. The other professor will beat me up. So when is the next class starting? Usually 10 o'clock, is it?
Yes, sir.
Okay. Yeah. So
Sir,
yes.
I'm seeing through gyros, and there is something called drift of the gyro that is a big problem. So
Right.
is it by the friction?
Yeah, all those issues are there. That means gyros cannot measure the same quantity in the same way. So it will start measuring different things at different times. That is called drift of the gyro. So we are not talking about sensors now. All are ideal quantities because we are introducing only the fundamentals. So when we discuss the basics of sensors, that time we will introduce, there is something called drift that is across different times when you measure, or the same values, if you keep on rotating with respect to some rate, let us say 10 degrees per second, it will not measure 10 degrees per second, but it will keep on changing. So that is called drift of the gyroscope. The drift, whatever change is there when you integrate, because that is encountered in your measurement, the acceleration will indicate it indirectly. So that will give you a wrong navigation solution. These are one of the most fundamental difficulties in these inertial sensors. They all have drifts. They don't measure precise value first. It is not only fixed by us, it also has a drift. So there are many kinds of drifts. If you switch on and switch off, it will measure different things at different switch on, switch off. And if you keep it on in the same measuring inputs, then also the values will change. So these are all physical phenomena which we don't understand well. So they are only mathematically modeled. Yes, drift is a major problem in these inertial sensors. That is why the integrated navigation system is finding a wider application. So you need external source once in a while, and then when that external source is not available, you should be able to do it yourself.
Got it.
Okay, so I'm going to stop before your next class starts. So you can always write to me, or in the next class we will discuss this again. Okay.
Sir, can you please
sir?
share the slides?
I think I have shared it. I hope
Okay,
this
sir.
will work. Okay, thank you.
Sir, are there any reference books for this?
These are just from the internet. There are many books. I will. Okay, next class you just remind in the beginning. I will tell you,
Okay, sir.
or I will try to include it in the Moodle itself.
Thank you, sir.
Thank you. Have a good day, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.